to Astronomy in Space. In this program we take a look at the highlights of a July night sky. Our main theme is the Sun in action and NASA's new spacecraft IRIS, which will launch on Thursday to study the Sun's atmosphere in fine detail. We also take a look at the launch of Shenzhou-10, China's fifth ever manned mission to successfully lift off on the 11th of June. But first, the summer solstice on June the 21st brought with it the first days of summer and the longest day, which was just shy of 16 hours 35 minutes long, while the Earth continued to move further away from the Sun. Aphelion occurs on July the 5th, when the Earth will be at its greatest distance from our nearest star, which is 94.5 million miles. The Earth is the third planet out from the Sun and is tilted over on its axis by 23.5 degrees to the plane of its orbit. Now, take a look at the photograph behind me. It's called the analemma. Analemma photographs are made by taking a picture of the Sun from the same place at the same time of day once a week, generating 30 to 50 frames. The Sun makes this shape over a year because the Earth rotates on a slightly different axis to that of the Sun, and our planet also travels on an elliptical orbit. As one hemisphere of Earth tilts further from the Sun, the arc of the Sun's daily path seen from that location lowers towards the horizon. The Sun's arc then gets higher in the sky as the tilt reverses. The Sun's highest point in the sky, seen in this analemma, occurs during the summer solstice, while its lowest point during winter solstice. This is a good way to illustrate the changing seasons. The nights are now beginning to get shorter again. The sun rises at 4:44 AM and sets at 9:33 PM on July the 1st, with the sunrise at 5:21 AM and sunset at 9 PM at the end of the month. Weather permitting, the best time to start stargazing is from 10 PM onwards. The phases of our moon this month begin at last quarter on June the 30th, new moon on July the 8th, first quarter July the 16th, and full moon on July the 29th. As the moon travels across the night sky on its daily journey, there will be photo opportunities. Mars will be 4.2 degrees north of the moon on July the 6th, and Jupiter will be 4.3 degrees north of the moon the following day. Saturn will be 4.2 degrees north of the moon on the 17th of July. Also, our moon will have a close encounter with the bright star Spica in Virgo on July the 16th, the angle of separation being only 0.4 degrees. This month, Mercury is at inferior conjunction on July the 9th and is therefore not visible. Venus is now lower in the western sky after sunset, shining at magnitude -3.8 and sets around 10:30 PM. Throughout July, Venus may be seen 7 degrees above the west-northwest horizon. From the middle of the month, the planet Mars is visible in the eastern sky around dawn. At the beginning of July, Mars shines at magnitude +1.8 in the constellation of Gemini, the Twins. It rises at 3:28 AM, more than 40 minutes before sunrise. By the end of the month, this gap will have widened to almost 2.5 hours. Mars is a difficult planet to observe without a moderate-sized telescope, and its small orange disk can be glimpsed. However, if you are awake early enough, you will have much better luck with the giant planet Jupiter nearby. Jupiter also lies in Gemini, rising about half an hour after Mars, and is much brighter at magnitude -1.7. Both Mars and Jupiter lies close to the star Eta Gemini, also known as Propus, and the nice open cluster Messier 35. Even a pair of binoculars will show the planet's disk and 4 bright moons: Io, Europa, Ganymede, and Callisto. A small telescope will show the horizontal cloud bands across the Jovian disk and the planet's moons changing their daily positions around the planet. Jupiter is 88,700 miles in diameter and is the fifth planet in order of distance from the Sun at 483 million miles. It takes 11.8 Earth years to orbit the Sun once, while the planet's clouds indicate a day less than just 9 hours 55 minutes. The ring planet Saturn is still on view in the constellation of Virgo. It shows a magnitude plus 1.0. The planet sets at 1:43 AM on July the 1st and 23:44 PM at the end of the month. Of course, the planet's glorious rings are still on view in small telescopes. Now let us see what constellations are on view this month. During July evenings, the plough may be seen high overhead, standing on its tail, and is a good signpost to nearby constellations. The two stars in the bowl of the plough are named Merak and Dubai, and are known as the pointers. Follow them across the sky towards the west, and you'll come to Polaris, the pole star in Ursa Minor, with Little Bear. Polaris lies directly above the Earth's north pole and remains almost stationary in the sky. It acts like the hub in a wheel, as all the other stars move around it once every day. Continue a line further still, and we arrive at the W-shaped constellation of Cassiopeia, the Queen, a distinct pattern of stars which lies in the Milky Way. High up in the southeast, you will find the three constellations that make up the Summer Triangle: Deneb in Cygnus, Vega in Lyra, and Altair in Aquila. Here again, Cygnus the Swan and Aquila the Eagle also lie in the Milky Way. By sweeping along the star clouds of the Milky Way with a pair of binoculars, you will spend a nice evening looking at the many star clusters and nebulae on view. There are two constellations to look out for this month: Hercules overhead with its keystone pattern of stars to the right of the bright star Vega in Lyra. It contains the bright globular cluster Messier 13. The other is Andromeda, just rising over the northeastern horizon, in which you will find the Andromeda Galaxy, Messier 31. This deep sky object is easily visible in binoculars, yet it lies over 2.2 million light years away. Now, go back to the plough and follow the handle of the star down into the southwest, and you'll come to the bright orange star Arcturus in Boots, the herdsman. Follow the line further still, and you will arrive at the bright planet Saturn in Virgo. All of the stars visible in the night sky come in various sizes, from supergiants to white dwarfs. They also have different temperatures, from blazing blue-white stars like Rigel in Orion, which comes in at 28,000 degrees, to cool red supergiants like Betelgeuse, also in Orion, which is less than 3,000 degrees centigrade. This brings us on to our main theme. Clear skies permitting, look up into the daylight sky, and the sun can be seen shining brilliantly. It is the nearest star to the Earth. Our sun is an incandescent ball of glowing hydrogen gas, 865,000 miles in diameter. In its core, hydrogen atoms are being transformed into helium at an enormous rate. As it does so, light is given off and the sun loses mass. The sun is losing 4 million tons every second. But don't worry, the sun has enough material to keep it shining for another 5 billion years. In the sun's core, the temperature is 15 million degrees centigrade, and like thermal patterns through your cup of coffee, this dissipates away to 6,000 degrees at its gaseous surface. In terms of structure, the sun has a central core where the nucleus fusion takes place, the radioactive zone followed by the convection zone, where heat and charged particles move up to the sun's visible surface. The visible surface layer is called the photosphere. This is where we find dark spots. These are often saucer-shaped depressions that astronomers call sunspots. They have been observed ever since the invention of the telescope in 1610. The Italian astronomer Galileo Galilei being the first person to see them. A word of warning: on no account would you look directly at the sun with either binoculars or a telescope. Focusing all that light and heat onto your eyes will cause a lot of damage and a permanent loss of your eyesight. So please don't be tempted. The best thing to do is to project the image of a sun's disk onto a piece of card behind the eyepiece. Using this method, you can draw the sunspots and follow them across the sun's disk over time. Today, NASA have two spacecraft in orbit studying the Sun in detail: the Solar Dynamics Observatory, SOHO, and the Stereo mission, which show the Sun in many different wavelengths of light on an hourly basis. All of these images can be seen free of charge over the internet, which makes observing the Sun really safe, even for school children. Observing these sunspots show that the polar regions of the Sun rotate in just 25 Earth days, and the equatorial band in 27 Earth days. The number of sunspots varies over an 11-year cycle, and at present we are at sunspot maximum, so in theory there should be many on view. Around sunspots are strong magnetic fields which wind and twist around until they break, sending huge plumes of hot gas into the Sun's lower atmosphere. We call these solar flares or prominences, and they occur quite often. However, solar flares are only visible through special filters that show the Sun in light of hydrogen. The Sun's atmosphere is called the chromosphere, and the temperature here climbs to over 1 million degrees centigrade, and astronomers are not quite sure why this is. Heat in physics is defined as energy transferred by thermal interactions. Heat flows spontaneously from hotter to colder systems. When two systems come into thermal contact, they exchange energy through the microscopic interactions of their particles. When the systems are at different temperatures, the result is a spontaneous net flow of energy that continues until the temperatures are equal. At that point, the net flow of energy is zero, and the systems are said to be in thermal equilibrium. There are two kinds of heat flow. Put an iron poker into a hot fire until the end glows white hot, and you are witnessing thermal heat. Now, turn on a 2-bar electric fire, and the heat can be felt radiating away. That's latent heat. It's the same with the Sun. The Sun's chromosphere is full of atoms that are wide in space, so the temperature is high, but the heat is actually low. On Thursday, June the 27th, NASA will launch its new solar observatory called IRIS, the Interface Region Imaging Spectrograph, from the Goddard Space Flight Center. Its primary goal is to understand how heat and energy move through the lower levels of the solar atmosphere. IRIS is a class of spacecraft called a Small Explorer, which NASA defines as costing less than $120 million. IRIS weighs 440 pounds. It is approximately 7 feet long, and with its solar panels extended, is a little over 12 feet across. The telescope's primary mirror has a diameter of about 8 inches, while it will only be able to see about 1% of the Sun at any one time. It will be able to resolve that image to show features that are as small as 150 miles on the Sun. Such high resolution will serve as a microscope for larger instruments that capture images of the whole Sun simultaneously. IRIS will collaborate with NASA's Solar Dynamics Observatory, for example, to target active regions of the Sun. Adrian Dorr is the Deputy Project Scientist with the IRIS team. Here he explains the purpose of the mission.
The secrets of the Sun are hidden in how energy travels up through its layers out into space. The Sun's energy starts in its core, a giant fusion engine where hydrogen atoms are turned into helium atoms. The energy produced there moves up through the convection zone to the Sun's surface, the photosphere. Moving magnetic fields contribute extra energy along the way. As energy moves outward, the temperature continually drops. This is just as one would expect while moving away from a heat source.
Up until that point, everything makes sense in that the hottest part is in the middle and everything gets gradually cooler as we move away. But then something very interesting starts to happen, which is that it starts to get hotter again.
This layer, where the temperature mysteriously begins to rise again, is called the chromosphere. It lies in an interface region between the photosphere and the corona, the hottest and outermost region of the Sun's atmosphere. Observations from the IRIS mission will help distinguish among numerous theories on how the corona is powered.
IRIS will show the solar chromosphere in more detail than has ever been seen before. It will be taking images and spectra of specifically chosen wavelengths of ultraviolet light, and these will be the highest resolution and perhaps more importantly at a more rapid rate than has ever been done before.
The interface region is the greatest source of ultraviolet light that impacts the Earth and the space around it. Only a specifically designed spacecraft can image the wavelengths of light needed to study the chromosphere. Advanced computer modeling will enable scientists to interpret the data and better understand how the energy moves through the chromosphere.
The light from the chromosphere is difficult to interpret because of the complicated interaction that the light has with the matter. It bounces around, if you will, many times before its final bounce towards us. And this means that that interaction between light and matter needs to be modeled in great detail, due to not just advances in computational power of computers, but in the computational techniques that have been developed by the IRIS team. We are in a position to do this.
It takes only a small fraction of the chromosphere's energy to power the corona.
Although the corona is extremely hot, millions of degrees, it's at a low density, so it doesn't actually take a lot of energy to heat it to that temperature. The chromosphere, on the other hand, is a much higher density, albeit lower temperature. And there's much more energy deposited in the chromosphere than the corona. So that a tiny fraction of that energy in the chromosphere escaping into the corona is plenty to power all of the processes that we see, from heating to such extreme temperatures to driving the solar wind that fills the whole solar system, impacting all the planets, including our own. We hope to better understand these fascinating and important processes with IRIS.
Now, Shenzhou 10, China's fifth manned spaceflight, launched successfully on June 11th on the Long Mach 2F rocket. Liftoff occurred at 9:38 UTC from the Jiuquan Satellite Launch Center. Shenzhou 10 approached and docked with the Tiangong 1 docking target, which launched in September 2011. They will be the last crew to dock with the Tiangong 1 before it is deorbited. Shenzhou 9 docked back in June 2012. Here is a film of the launch.
30秒。20秒。10、9、8、7、6、5、4、3、2、1。 点火！起飞，起飞，1点17时38分02秒，666毫秒，1点17时38分02秒，666毫秒，有缘，程序转弯，东风，程序转弯，东风，程序转弯。 USB 跟踪正常，遥控信号正常，主权光学跟踪正常，双筒光学雷达跟踪正常，东风光学雷达跟踪正常，遥测信号正常。 东 东风光学 USB 雷达跟踪正常，遥测信号正常，东风飞行正常。
9圈逃逸塔分离，
东风逃逸塔分离，逃逸塔分离，
逃逸塔分离。
青山 USB 跟踪正常，遥测信号正常。深城光学雷达跟踪正常。9圈助推器分离，
东风助推器分离，助推器分离，
助推器分离。
9圈1、2级分离，
东风1、2级分离，1、2级分离
，1、2级分离
，1、2级分离。渭南 USB 雷达发现目标。
东风光学雷达跟踪正常，遥测信号正常，东风飞行正常。
9圈抛整流罩，深城抛整流罩，
东风抛整流罩，
抛整流罩。
东风光学雷达跟踪正常，遥测信号正常，东风飞行正常。
渭南 USB 雷达跟踪正常，光学雷达跟踪正常，
遥测信号正常。
青山 USB 跟踪正常，遥测信号正常。渭南飞船双向捕获，
东风飞行正常。
太原雷达跟踪正常，遥测信号正常。
雷达建遥发现目标。
东风光学雷达跟踪正常，遥测信号正常。
太原雷达
建遥
跟踪正常，
遥测信号
正常。
青山 USB 跟踪正常，遥测信号正常。渭南 USB 雷达跟踪正常，深城光学雷达跟踪正常。
Shenzhou 10 are Commander Ni Heng, Zhang Exi Huang, and second Chinese female astronaut Wang Yaping. They stayed in orbit for just 2 weeks before successfully returning to Earth. That's all we have time for this week. Thank you for watching. Until next time, goodbye for now.